Imagine scientists confirm tomorrow that a molecule has been detected in the atmosphere of a planet 124 light-years from Earth. A molecule that on Earth means one thing, and one thing only: marine life. And the confidence level attached to that detection is 99.7%. You read the headline, you feel something shift. You assume the word confirmed is coming next. It's not coming. 99.7% is not confirmed. The number sits in a results table in a 14-page paper that most people never read. The press release calls the finding tentative. The scientists who produced it call the molecule potential. And what they cannot call it, without contradicting their own data, is absent. Because the molecule is there. In the atmosphere of K218b 124 light-years from here, dimethyl sulfide, a compound that no known non-biological process has been demonstrated to produce at those concentrations, returned 99.7% confidence. Not tentative, not potential, 99.7%. Tonight we go through what that number actually means, why the scientists who produced it are still calling it careful, what the molecule is and why it points in only one direction, how far 124 light-years actually is when you put it in human terms, and what the honest verdict looks like when you strip the caution language and read only what the data says. Subscribe before we continue. It helps this channel reach more people who want exactly this kind of investigation. We begin. The statement they would not make, September 2023, the Astrophysical Journal Letters, page 5, table 2. A peer-reviewed results table showing the retrieved molecular abundances for the atmosphere of K218b, published by Niku Madhusudan at the University of Cambridge. Carbon dioxide detected. Methane detected. Dimethyl sulfide detected at 99.7% confidence, not in the abstract, not in the press release, in the table. The abstract said tentative evidence. The press release said potential biosignature. The table said 99.7%. All three documents were describing the same number. Two of them chose their words carefully. One of them couldn't. The gap between tentative and 99.7% is not rhetorical. It reveals something specific about how science communicates when the stakes of interpretation are categorically different from the stakes of detection. The detection was clear. The interpretation of what the detection means, that's what remains open. Madhusudan's team used cautious language for the interpretation, while their own data sat at 99.7% for the signal. Both statements were honest. They were describing different things. Let us deconstruct what 99.7% actually means before anything else. 3 sigma. That is the name for it in statistics. It means the signal sits 3 standard deviations above the background noise level. The probability that you are seeing a random fluctuation rather than a genuine molecular detection is 0.27%. Roughly 1 in 370. That's not a weak finding. That is the confidence level at which the particle physics community began treating the Higgs boson as real. In December 2011, both detectors at the Large Hadron Collider reported Higgs signals at approximately 3 sigma. The scientific community restructured research programs around a 3 sigma Higgs. 7 months later, 5 sigma confirmed it. 3 sigma had been right. That is what 99.7% means as a starting point, before the caveats, before the follow-up, before the MIRI data. It means credible, serious, and not yet finished. The institutional context matters. Cambridge's Institute of Astronomy has been at the forefront of exoplanet atmospheric science for over a decade. Madhusudan's group developed and refined the atmospheric retrieval techniques that make transmission spectroscopy possible, starting with Hubble Space Telescope data before Webb launched. The retrieval code that returned the DMS signal had been validated on dozens of prior exoplanet atmospheres. When a well-validated tool applied by an experienced group to high-quality data returns 99.7%, the result carries weight that the same number from a first-pass analysis by a new team wouldn't. The team knew exactly what their code could and couldn't do. The 99.7% was not a surprise to them. It was a number they understood in detail and chose to report as tentative anyway. The peer review process at the astrophysical journal Letters involves external reviewers who evaluate both the methodology and the statistical claims independently. The K2-18b paper was revised during review to address referee concerns before publication. The 99.7% in the published version is not the number from the first draft. It's the number that survived the full review process. That distinction matters when evaluating how much institutional weight the finding carries. Why tentative if the number is 99.7%? Because in 2020, a team announced the detection of phosphine in the atmosphere of Venus at roughly 15 sigma. 15. That was the significance claimed in the original paper. Global headlines followed. Within weeks, independent researchers found systematic calibration errors in the data processing pipeline. When the errors were corrected, the signal dropped to approximately 1 sigma. Near non-detection. The original team issued a correction. What had been announced as a 15 sigma discovery became a claim below the detection threshold. It was not fraud. It was the failure mode of a high-stakes science. A signal in complex data interpreted before the systematic checks were complete. Madhusudan's team knew that episode intimately. Their paper explicitly referenced Venus phosphine as motivation for additional caution. They applied multiple independent retrieval codes to the K2-18b data. They ran sensitivity tests. They chose the word tentative because they understood what the alternative cost. A confirmed then retracted biosignature announcement would damage the field's credibility for a generation. Their caution was professional responsibility, not scientific timidity. So here is where the false hope ladder begins. 99.7% feels like certainty. The press release language explains why it's not confirmed yet. You think, more data arrives and we will know. Then the molecule itself enters the picture and the ladder shifts under you. The number was real. The headline was written around it. What produced that number? The instrument, and understanding how Webb detects atmospheric chemistry at 124 light-years requires setting aside one assumption about what space telescopes do. The paper was published in September 2023. The lead author was Niku Madhusudan, a planetary scientist at the University of Cambridge who spent his career developing the atmospheric retrieval techniques that make exoplanet spectroscopy possible. It appeared in the astrophysical journal Letters, a peer-reviewed publication with rigorous standards and a reputation for rapid turnaround communications of significant observational results. This was not a preprint server posting. It was a paper that independent experts had evaluated and judged methodologically sound before it reached the public. The paper was 14 pages long in its published form. Most of those pages were methods: atmospheric retrieval methodology, data reduction pipeline description, statistical framework, sensitivity tests, comparison of different retrieval codes. The detection of dimethyl sulfide appeared in the results section. The language around it was deliberate. The number attached to it was 99.7% in the body of the paper, not the abstract, not the press release. In the body of the paper, in a table summarizing the retrieved molecular abundances and their confidence levels. The abstract used phrases like tentative evidence and potential biosignature. The table used a number. That gap between the language chosen for the abstract and the number sitting in the results table is worth spending time with before anything else. 3 sigma. That is the statistical name for 99.7% confidence. It means the signal sits 3 standard deviations above the background noise level. 1 sigma, about 68% confidence, means you have seen something that might be real. 2 sigma, about 95%, means you have probably seen something real. 3 sigma means the probability that you are seeing a random fluctuation rather than a genuine signal is approximately 0.27%, less than 3 in 1,000. In 2011, the Large Hadron Collider reported Higgs-boson signals at approximately 2.5 to 3 sigma from both primary detectors. The particle physics community didn't dismiss these signals, they restructured research programs around them. They commissioned more analysis. They allocated additional accelerator running time to expand the data sets. 7 months later, in July 2012, both detectors reached 5 sigma. The Higgs was confirmed. 3 sigma had been telling the truth, but it had not been definitive. That distinction is the entire heart of the K218b story. In everyday life, 99.7% is as close to certain as most consequential decisions ever require. A drug approved at 99.7% confidence of efficacy would be prescribed by physicians worldwide. A structural engineering analysis returned at 99.7% confidence would be acted on without hesitation. If a flight safety rating were 99.7%, you would board without hesitation. The number is large enough to feel decisive and specific enough to feel scientific. In particle physics, 99.7% is not enough to call something real. The history of particle physics is littered with 3 sigma signals that dissolved when more data was collected. The 5 sigma standard exists specifically because 3 sigma was demonstrably insufficient to prevent false positives from reaching the literature. The field learned this through painful episodes of announced discoveries that subsequently collapsed, and it raised its bar accordingly. So why tentative? Because in 2020, a team announced the detection of phosphine in the atmosphere of Venus at roughly 15 sigma. 15. That was the significance claimed in the original paper. It generated global headlines. Within weeks, independent researchers found systematic calibration errors in the data processing pipeline. When corrected, the signal dropped to approximately 1 sigma, near non-detection. What had been announced as a 15 sigma discovery became a claim below the detection threshold. It was not fraud. It was the failure mode of high-stakes science, a signal in complex data interpreted before systematic checks are complete. Madhusudan's team knew that episode well. Their paper explicitly referenced Venus phosphine as motivation for additional caution. They applied multiple independent retrieval codes to the K2-18b data. They ran sensitivity tests. They chose the word tentative because they understood the cost of a false positive at this scale. A confirmed then retracted biosignature announcement would damage the field's credibility for a generation. Their caution was professional responsibility, not scientific timidity. The institutional context matters here. Cambridge's Institute of Astronomy has been at the forefront of exoplanet atmospheric science for over a decade. Madhusudan's group developed and refined retrieval techniques specifically for Hubble Space Telescope transmission spectra before Webb launched. They were not learning transmission spectroscopy on K2-18b. They were applying a mature methodology to a new dataset with a better telescope. The retrieval code that returned the DMS signal had been validated on dozens of prior exoplanet atmospheres. When a well-validated tool applied by an experienced group to a high-quality dataset returns 99.7%, the result carries more weight than the same number from a first-pass analysis by a new team on a new instrument. One more piece of context that most coverage missed. In the K2-18b paper, the word tentative applies specifically to the DMS detection, not to the detections of methane and carbon dioxide. Those 2 molecules were reported with higher confidence levels and without the tentative qualifier. The selectivity of the qualifier is itself informative. Madhusudan's team was not broadly hedging all of their results. They were specifically hedging the DMS result because it was the result with the most significant potential interpretation and the largest gap between the detection and a fully airtight case. The precision of where they applied the caution tells you something about how they understood the strength of each individual result. But the 99.7% stayed in the paper. It couldn't be removed without misrepresenting the retrieval results. It sat in the table alongside carbon dioxide and methane, with the retrieved abundance and confidence level written plainly. The number was real. The headline was written around it. The gap between tentative and 99.7% also reveals something about how science communicates when the stakes of interpretation are asymmetric. In domains where a false positive costs relatively little, 3 sigma is treated as decisive without apology. Medical imaging studies routinely publish 3 sigma results as significant findings. Financial risk models flag 3 sigma events as actionable warnings. But in the specific case of atmospheric biosignature detection, a false positive wouldn't merely result in a correction to the literature. It would reshape government funding priorities for the search for extraterrestrial life, influence how the public understands the probability of life beyond Earth, and potentially set back the credibility of the entire biosignature detection field for years or decades. The calibration of that caution was itself a scientific judgment. Madhusudan is not a newcomer to this field. His group at Cambridge developed and refined many of the atmospheric retrieval techniques that make exoplanet spectroscopy possible, starting with Hubble Space Telescope data and continuing through the Webb era. The retrieval code that returned the DMS signal had been validated on dozens of prior exoplanet atmospheric datasets before it was applied to K218b. When a well-validated tool applied by an experienced group to high-quality data returns 99.7%, the result carries more weight than the same number from a first-pass analysis on a new instrument by a team learning its capabilities. One more piece of context that most coverage missed. In the K2-18b paper, the word tentative applies specifically to the DMS detection, not to the methane or carbon dioxide detections. Those 2 molecules were reported with higher confidence levels and without the tentative qualifier. The selectivity of the qualifier is itself informative. The team was not broadly hedging all of their results. They were specifically hedging the DMS result because it was the result with the most consequential possible interpretation and the largest remaining gap between the detection confidence and a fully airtight interpretive chain. What makes the K218b finding stand apart from other candidate biosignature claims is the convergence of independent factors. It's not just that DMS was detected. It is that DMS was detected at 3 sigma confidence in the atmosphere of a planet in its star's habitable zone, consistent with a Hessian structure that could support a marine biosphere, by the most capable infrared telescope ever built, in a peer-reviewed paper from one of the leading groups in atmospheric retrieval science, with multiple independent reanalyses finding the signal present, and with follow-up observations finding the signal not refuted. Any one of these factors alone would be noteworthy. All of them together is what makes the number significant in context. The press release and the paper exist in tension because they serve different audiences with different needs. Scientists communicate to the public through simplification, and simplification requires choosing which uncertainty to foreground. The team chose to foreground the uncertainty in interpretation, which is the scientifically correct choice, because interpretation is where the genuine open question lives. They couldn't remove the 99.7% from the paper without misrepresenting their own results. The tension between the press release language and the results table number is what makes understanding this story require reading both documents, rather than either one alone. The temporal context also matters. The K218b paper appeared in September 2023, when Webb had been conducting science operations for just over a year. The fact that multiple independent groups working with the same raw data but different pipelines all found the DMS signal present at varying confidence levels, rather than some finding it and some not finding it at all, suggests the signal is genuinely in the data rather than being an artifact of any single group's analysis choices. That consistency across pipelines is a form of robustness check that the original paper alone couldn't provide. What the light left behind Webb doesn't photograph K218b. That is the first thing to understand. No image of K218b exists from Webb or any other telescope. The planet is 124 light-years from Earth, roughly 2.6 times Earth's radius. The angular size it subtends at Earth is roughly 0.00008 arc-seconds. The Hubble Space Telescope's resolution limit at visible wavelengths is approximately 0.05 arc-seconds. K218b's angular size is roughly 600 times smaller than Hubble's resolution limit. Resolving it as more than a point source would require a mirror approximately 1.4 kilometers across, operating in space. No such instrument exists or is planned. Webb doesn't look at K218b, it looks through K218b. When K218b passes in front of its host star K218 during transit, the planet's atmospheric limb is backlit by the star. Starlight that passes through the atmospheric ring on its way to Webb's detectors is partially absorbed by whatever molecules are in the atmosphere. Different molecules absorb different wavelengths of light with a precision that allows unambiguous identification. Carbon dioxide absorbs at 4.3 micrometers. Methane has features at 3.3 and 7.7 micrometers. Dimethyl sulfide has absorption features near 3.4 and 9.5 micrometers. Webb measures the star's spectrum before, during, and after transit. The difference between the baseline and the in-transit spectrum at each wavelength is the transmission spectrum of the atmosphere. It's the fingerprint the atmosphere pressed into the starlight. To understand the precision this requires, the atmospheric layer producing the signal is perhaps 100 to 200 kilometers thick. The planet's radius is 16,000 kilometers. The planet's cross-section is small relative to the star. The star is 124 light-years away. The changes in light intensity corresponding to atmospheric molecular absorption at this distance are measured in parts per million. Webb resolves them because its primary mirror is 6.5 meters across, roughly 7 times the light-collecting area of Hubble. It operates in the infrared, where molecular features are most distinct. It sits at the L2 Lagrange 1.5 million kilometers from Earth, in a thermally stable environment, where its detectors are cooled to within a few degrees of absolute zero. The K218b observations use 2 transit events with Webb's NIRSpec instrument, covering wavelengths from 0.97 to 5.27 micrometers. Each transit lasts a few hours. The data from 2 transits were combined and fed into an atmospheric retrieval algorithm that tested thousands of possible atmospheric compositions and calculated which best matched the observed spectrum. Dimethyl sulfide was not pre-selected. It emerged as a best fit component. This is not a process that can be manipulated by wishful thinking. The algorithm returns the best fit to the data. The data returned 99.7%. There is a potential complication worth naming: the transit light source effect. K2-18 is not a uniform disk of light. Like all stars, it has surface features, star spots and faculae, regions of different temperature and brightness. If these features are in the path of K2-18b's transit chord across the stellar disk, they can imprint their own spectral signatures onto the transmission spectrum in ways that mimic molecular absorption. Madhusudan's team modelled stellar contamination and found it couldn't explain the DMS feature. The spectral shape and wavelength were inconsistent with the expected signatures of star spots at K218's temperature. But stellar contamination modelling requires assumptions about the distribution of active regions on K218's surface that cannot be directly verified. This is one reason the MIRI follow-up at 9.5 micrometers is important. Systematics affecting near-spec at 3.4 micrometers are unlikely to produce the same artifact in a different instrument at a completely different wavelength. Understanding how data from Webb reaches the science community is also worth a moment. After each transit observation, the raw detector data is transmitted from the spacecraft at L2 to ground stations, processed through the Space Telescope Science Institute standard reduction pipeline, and eventually made available through the Mikulski Archive for Space Telescopes. The typical delay between observation and public data availability for guest observer programs is roughly a year for proprietary data, during which only the principal investigators team can access it. After the proprietary period ends, any researcher worldwide can download and analyze the same data. The K218b original transit data was released after the Madhusudan team's paper appeared, enabling the independent reanalyses that followed. Independent groups applying different pipelines to the same raw data have found results ranging from consistent with the original 99.7% to confidence levels somewhat below 3 sigma. No published independent reanalysis has returned a confident non-detection. The signal is present across multiple analyses. The debate is about its strength, not its existence. That is a meaningfully different situation from one where some analyses find the signal and others do not find it at all. To make the precision concrete using the DNA's scale translation chain, NeoSpec at 3.4 micrometers can resolve features separated by roughly 0.034 micrometers. A DMS absorption feature in that region spans roughly 0.1 to 0.2 micrometers, wide enough for prism resolution to capture the shape, not just the presence. The absorption signal itself, at 124 light-years, represents a change in starlight intensity during transit of roughly 10 to 50 parts per million at the relevant wavelengths. 10 parts per million. That is equivalent to detecting a single drop of ink dissolved in a bathtub of water from across a room using only the color change in a narrow band of light. Webb does this. It does it because it was engineered specifically to. The light left K218b's atmosphere during its transit. It travelled 124 light-years. It arrived at a mirror in space. The mirror recorded the missing wavelengths. The algorithm processed those absences. The table showed 99.7%. The instrument found it. What it found next changes everything about how to read that number. Webb does not photograph K218b. No image of K218b exists from Webb or any other telescope. The reasons are fundamental. K218b is 124 light-years from Earth. Its radius is approximately 16,000 kilometers. The angular size it subtends at Earth is roughly 0.00008 arc-seconds. The angular resolution of the Hubble Space Telescope at visible wavelengths is approximately 0.05 arc-seconds. K218b's angular size is roughly 600 times smaller than Hubble's resolution limit. To resolve K218b as more than a point source would require a mirror approximately 1.4 kilometers across, operating in space. No such instrument exists or is planned. There is also the contrast problem. K218 is approximately 1 million times brighter than K218b at relevant wavelengths. Separating the planet's reflected light from the star's direct light at the angular separation K218b sits from its star, roughly 0.03 arc-seconds at maximum elongation as seen from Earth, is beyond the coronagraphic capability of any currently operating telescope for a planet at this distance. The planet is lost in the star's glare. Direct imaging is not an option. Webb reads the shadow the atmosphere leaves in starlight. K218b orbits K218 at an inclination such that, as seen from Earth, the planet passes directly in front of the star once every 32.94 days. This is a transit. During a transit, the planet blocks some of the star's light. The fractional dimming, the transit depth, is approximately 2.7% for K2-18b. But Webb does something transit photometry alone cannot. It measures how much light the planet's atmosphere absorbs at each wavelength separately. During transit, a thin ring of the planet, the atmospheric limb, is backlit by the star. Starlight passing through this ring is partially absorbed by whatever molecules are in the atmosphere. Different molecules absorb at different wavelengths with a precision that allows unambiguous identification. Carbon dioxide absorbs at 4.3 micrometers. Methane has features at 3.3 and 7.7 micrometers. Dimethyl sulfide has absorption features near 3.4 and 9.5 micrometers. Webb measures the star's spectrum before, during, and after transit. The difference between the baseline and the in-transit spectrum at each wavelength is the transmission spectrum of the atmosphere. It's the fingerprint the atmosphere pressed into the starlight. This technique is called transmission spectroscopy. The K218b observations use two transit events with Webb's NIRSpec instrument, covering wavelengths from 0.97 to 5.27 micrometers. The combined data was fed into an atmospheric retrieval algorithm that tested thousands of possible atmospheric compositions and calculated which best matched the observed spectrum. Dimethyl sulfide was not pre-selected. It emerged as a best fit component. The algorithm returned 99.7% confidence. There is a potential complication worth understanding: the transit light source effect. K218 is not a uniform disk of light. Like all stars, it has surface features including star spots and faculae, regions of different temperature and brightness. If these features happen to be in the path of K218b's transit chord, they can imprint their own spectral signatures onto the transmission spectrum in ways that mimic molecular absorption. Madhusudan's team modelled stellar contamination and found it could not explain the DMS feature. The spectral shape and wavelength were inconsistent with the expected signatures of star spots at K218's temperature. But stellar contamination modelling requires assumptions about the distribution of active regions on K218's surface that can't be directly verified, which is one reason the MIRI follow-up is important. Webb's design represents the integration of lessons from every space observatory that preceded it. The Hubble Space Telescope, launched in 1990 with a flawed primary mirror that required a correction mission in 1993, taught the engineering community that on-orbit servicing is technically possible, but enormously expensive. Webb was designed from the outset to be unserviceable because it operates at L2, beyond the reach of any crewed spacecraft currently in the fleet. That design constraint forced engineers to build higher initial reliability and more robust redundancy than any previous space observatory. That Webb deployed correctly and has been operating nominally since its first light observations in 2022 is itself a significant achievement, and the precision of its atmospheric measurements reflects this engineering investment. The near-infrared spectrograph used for the K218b detection can observe in two modes relevant to exoplanet work: a prism mode covering the full 0.6 to 5.3 micrometer range at lower spectral resolution, and several grating modes that cover narrower wavelength ranges at higher resolution. The K218b observations use the prism mode to get broad wavelength coverage in a single observation, which maximizes the number of molecules that can potentially be identified. Higher resolution modes would give more precise wavelength measurements for individual features, but at the cost of wavelength coverage. The prism was the appropriate choice for a broad atmospheric characterization where the composition was not precisely known in advance. The data reduction pipeline for Webb transmission spectroscopy is an active area of development. Research groups doing precision atmospheric characterization typically apply their own custom corrections on top of the standard Space Telescope Science Institute pipeline outputs. The K218b transmission spectrum was processed through Madhusudhan's group's custom pipeline. When independent groups applied different custom pipelines to the same raw data, they got somewhat different spectra and somewhat different retrieval results. This pipeline dependence is a general feature of transmission spectroscopy that the community is working to understand and reduce. The MIRI follow-up at 9.5 micrometers provides a partial test because systematic errors affecting near-spec data at 3.4 micrometers wouldn't generally produce the same artifact in MIRI data in a completely different wavelength range using different detector technology. The instrument found it. The light passing through K218b's atmosphere during two transit events travelled 124 light-years and arrived at a 6.5-metre mirror with the record of its atmospheric absorption intact. The 99.7% describes how well the DMS hypothesis explains what those photons showed. The molecule. That only one thing makes your brain is not designed to evaluate dimethyl sulfide. No human brain is. Humans evolved on a planet where dimethyl sulfide has exactly one source, at meaningful concentrations: marine life. The cognitive shortcut that connects the smell of the sea to the presence of living organisms has been accurate for every human being who has ever existed, because on Earth, that connection has never failed. It's not a bias. It is an empirically verified rule that has never needed an exception. The problem is that when you apply it to K2-18b, you're using a rule derived from a sample of one planet. Dimethyl sulfide. The formula is CH3SCH3, two methyl groups flanking a single sulfur atom. Molecular weight 62 grams per mole. Boiling point 37.3 degrees Celsius. Volatile enough to evaporate readily from an ocean surface into the atmosphere above it. Its odour is the organic sharpness behind the smell of the sea. That association is not accidental. On Earth, the primary source of dimethyl sulfide is marine phytoplankton. These are single-celled photosynthetic organisms that inhabit the sunlit surface layers of the ocean. They produce an intracellular compound called dimethyl sulfonionpropionate, DMSP, which serves as an osmolyte, helping cells manage salt concentration in seawater. When phytoplankton cells die or are eaten, the DMSP inside them is released into the surrounding water. An enzyme called DMSP lyase cleaves the DMSP molecule into two products, dimethyl sulfide and acrylate. The DMS diffuses from the ocean surface into the atmosphere. The global ocean produces approximately 20 to 40 million tons of dimethyl sulfide per year through this mechanism, 20 to 40 million tons per year. For scale, that is roughly equivalent to the total weight of 4 to 8 million adult elephants, produced every single year by organisms individually invisible to the naked eye, distributed across every ocean on the planet. The biological machinery doing this has been running for hundreds of millions of years. It predates the dinosaurs. It predates complex multicellular life. DMSP biosynthesis pathways appear across multiple domains of marine life, from bacteria to single-celled eukaryotes, suggesting the pathway evolved multiple times independently because DMSP is that useful. A molecule this ancient, this widespread, this deeply embedded in the machinery of life on Earth, found in the atmosphere of a planet 124 light-years away. Every time we've detected dimethyl sulfide in a planetary atmosphere at meaningful concentrations, we have been looking at Earth. The entire known dataset is one planet. one planet with life. The detection of DMS as a potential biosignature was specifically predicted before the K218b data was analysed. A 2022 paper in Nature Astronomy by Sarah Seeger and colleagues at MIT, published more than a year before Madhusudan's results, proposed DMS explicitly as a Webb biosignature target for Haitian worlds. The paper calculated that a biosphere comparable to Earth's marine phytoplankton, scaled to the ocean area of a typical Haitian world, would produce DMS concentrations detectable by Webb at 3 to 4 sigma in approximately 2 transit observations. The K218b detection arrived at almost exactly the predicted significance level, with almost exactly the predicted number of transit observations. The signal matched a prediction made before the data was collected, not proof, but the kind of consistency between prediction and observation that strengthens a hypothesis. Now the first step in the false hope ladder. Can't DMS arise without biology? Surely. Chemistry is complex, the universe is old. Sulfur compounds appear in volcanic gases, in interstellar clouds, in the atmospheres of multiple planets in the solar system. A molecule as structurally simple as dimethyl sulfide would seem like something nature might produce through many routes under many conditions. The ladder collapses. The most plausible abiotic pathway begins with hydrogen sulfide. In a reducing hydrogen-rich atmosphere, H2S can form through volcanism or atmospheric chemistry. H2S can react with methane under UV irradiation to produce methanethiol. Methanethiol can react with methyl radicals produced when methane is photolysed in the upper atmosphere to yield DMS. The reactions are real. They have been demonstrated in laboratory conditions. The problem is the rate. Laboratory measurements of DMS production from this pathway in reducing conditions, scaled to K2-18b's estimated atmospheric conditions and UV flux, produce steady-state atmospheric DMS concentrations between 1 and several orders of magnitude below what would be needed to generate the Webb signal. 1 order of magnitude is a factor of 10. Several orders of magnitude is a factor of 1,000 or more. The biological mechanism, DMSP production by marine organisms, enzymatic cleavage to DMS, volatilization into the atmosphere, is well characterized and operates at exactly the concentrations needed. No new chemistry required. The abiotic alternative requires the discovery of a previously unknown high-rate DMS production mechanism operating in conditions that have never produced it in any laboratory or natural analog environment studied to date. There is one more property of DMS that makes it a particularly clean biosignature: its atmospheric residence time. DMS is destroyed in days to weeks under typical atmospheric conditions. It cannot accumulate over geological time the way oxygen can. A detection of DMS is diagnostic of current ongoing production. A planet that once had life but lost it 1 million years ago would have no atmospheric DMS today. Whatever produced the K218b signal was active within the last few weeks before the light Webb analyze left the planet's atmosphere. The scientific conservatism in the press release was not protecting against a demonstrated alternative. It was holding open a door that no evidence has yet walked through, while the evidence has been consistently pointing in one direction. You probably assume there are multiple natural pathways to produce it. Chemistry is vast. Sulfur is the 10th most common element by mass in the cosmos. Sulfur compounds appear in volcanic gases, interstellar clouds, and the atmospheres of multiple planets in our solar system. A molecule as structurally simple as dimethyl sulfide would seem like something nature might produce through many routes under many conditions. The universe has had 13.8 billion years to try. That assumption is the only place the abiotic alternative lives, and it has no demonstrated mechanism capable of producing DMS at the concentrations the Webb detection implies. They produce, inside their cells, a compound called dimethyl sulfonopropionate, abbreviated DMSP. DMSP is an osmolyte that helps cells manage their internal salt concentration against the osmotic pressure of seawater. It also functions as a cryoprotectant, stabilizing proteins and membranes at cold temperatures, and may serve as an antioxidant and a deterrent against some grazers. When phytoplankton cells die or are eaten, the DMSP inside them is released into the surrounding water. An enzyme called DMSP lyase then cleaves the DMSP molecule into two products, dimethyl sulfide and acrylate. The DMS diffuses from the ocean surface into the atmosphere. The global ocean produces approximately 20 to 40 million tons of DMS per year through this mechanism. The breadth of organisms producing DMSP on Earth matters here. The DMSP-producing biochemical pathway appears across multiple domains of marine life, from bacteria to single-celled eukaryotes to some multicellular plants in coastal environments. This distribution across distantly related lineages suggests DMSP biosynthesis pathways have evolved multiple times independently, which points to DMSP being a broadly useful solution to a broadly encountered biological challenge: managing osmotic stress in saline environments. If life on K218b uses any analogous biochemistry for osmotic management, even if not identical to Earth's DMSP pathway, DMS could be a common byproduct of ocean life on any world where organisms use sulfur-containing compounds as osmolytes. The detection of DMS was specifically predicted before the K218b data was analysed. A 2022 paper in Nature Astronomy by Sarah Seeger and colleagues at MIT, published more than a year before the Madhusudhan team's results, proposed DMS explicitly as a Webb biosignature target for Hycean worlds. The paper calculated that a biosphere comparable to Earth's marine phytoplankton, scaled to the ocean area of a typical Hycean world, would produce DMS concentrations detectable by Webb at 3 to 4 sigma in approximately 2 transit observations. The K218b detection arrived at almost exactly the predicted significance level, with almost exactly the predicted number of transit observations. The signal matched a prediction made before the data was collected. The stability of DMS under K218b's atmospheric conditions is relevant in a specific way. On Earth, atmospheric DMS is destroyed primarily by reaction with hydroxyl radicals produced by the photolysis of ozone and water vapor in the presence of UV radiation. The lifetime of DMS in Earth's atmosphere is roughly 1 to 2 days. In K218b's hydrogen-rich atmosphere, there is very little ozone. The primary DMS destruction pathway would differ from Earth's. Under K218b's atmospheric conditions, DMS might be more stable than on Earth, which would mean a smaller biosphere could maintain the same atmospheric concentration. Alternatively, if K218's ultraviolet output is high enough to drive significant photolytic destruction, the biosphere would need to be more productive to maintain the observed signal. The detailed photochemical modelling of DMS stability in K218b's atmosphere has direct implications for estimating the minimum biosphere size required. Can DMS arise without biology? The most plausible abiotic pathway begins with hydrogen sulfide in a reducing atmosphere. H2S can form through volcanism and atmospheric chemistry. It can react with methane under UV irradiation to produce methanethiol, which can react with methyl radicals to yield DMS. The reactions are real chemistry, demonstrated in laboratory conditions. The organisms that produce DMS on Earth do so for reasons that have nothing to do with producing DMS specifically. DMSP is an accident of useful osmotic chemistry that happens to have DMS as a breakdown product. The organisms producing it are not trying to signal their presence to distant observers. They are managing salt concentrations in their cells, and DMS is a byproduct of the enzyme that cleans up DMSP when cells die or are consumed. This means life on K218b does not need to deliberately produce DMS. It needs only to produce sulfur-containing osmolytes that break down into DMS as a secondary product of cell turnover. The threshold for life to produce DMS is lower than the threshold for life to deliberately signal anything. The concentration of DMS implied by the Webb detection has specific implications for the size of any putative biosphere on K2-18b. On Earth, the global ocean produces 20 to 40 million tons of DMS per year from a marine phytoplankton biosphere with a total biomass estimated at roughly 2 gigatons of carbon. If K2-18b's ocean produces DMS at a comparable or higher rate, the biosphere responsible would need to have productivity comparable to Earth's entire marine system. This isn't a trivially small biosphere. Whether K2-18b has had sufficient time and appropriate conditions to develop a biosphere of this scale depends on factors the current data cannot fully constrain. The stability of DMS under K2-18b's specific atmospheric conditions is also relevant. On Earth, atmospheric DMS is destroyed primarily by reaction with hydroxyl radicals produced by the photolysis of ozone and water vapor. The lifetime of DMS in Earth's atmosphere is roughly 1 to 2 days. In K2-18b's hydrogen-rich atmosphere, ozone is nearly absent. Under K2-18b's atmospheric conditions, DMS might actually be more stable than on Earth, meaning a smaller biosphere could maintain the same atmospheric concentration. This would lower the threshold for the biosphere size required to produce the detected signal. The Sarah Seeger 2022 paper predicting DMS as a Webb biosignature target for Hycean worlds deserves one more mention. The paper was a pre-registration of sorts, a published prediction about what Webb should detect if Hycean worlds host biology, made before the relevant Webb data existed. The K2-18b detection arrived at almost exactly the predicted significance level, with almost exactly the predicted number of transit observations. The consistency between the prediction and the observation is not proof of biology, but it's the kind of consistency between prediction and observation that strengthens a hypothesis in a meaningful way. The breadth of organisms producing DMSP on Earth matters here. The DMSP producing biochemical pathway appears across multiple domains of marine life, from bacteria to single-celled eukaryotes. This distribution across distantly related lineages suggests DMSP biosynthesis pathways have evolved multiple times independently, pointing to DMSP being a broadly useful solution to a broadly encountered biological challenge: managing osmotic stress in saline environments. If life on K2-18b uses any analogous biochemistry for osmotic management, DMS could be a common byproduct of ocean life on any world where organisms use sulfur-containing osmolytes. One final consideration about the molecular identification: dimethyl sulfide is not the only sulfur compound that could potentially arise in K2-18b's atmosphere. The retrieval algorithm tested multiple sulfur-bearing molecules simultaneously and found that DMS produced a better fit to the observed spectrum than the alternatives. The confidence level of 99.7% is the confidence that including DMS in the atmospheric model significantly improves the fit compared to models without DMS. The molecular identification is based on the specific spectral shape of the DMS absorption band, which differs from other sulfur compounds at the wavelengths covered by NIR spec. The world beneath the hydrogen sky, K2-18b. You have heard it described as a planet in the habitable zone of its star, which is accurate. You probably picture something like Earth, a rocky world with an atmosphere, orbiting a star at a distance where liquid water is possible. That picture is wrong in almost every detail. K2-18b has a radius 2.6 times Earth's and a mass 8.6 times Earth's. The density implied by those two numbers is approximately 2.7 grams per cubic centimetre. Earth's mean density is 5.5 grams per cubic centimetre. Rock has a density around 2.7 to 3.5 grams per cubic centimetre. Water is 1 gram per cubic centimetre. K2-18b's bulk density is consistent with a planet composed largely of water or other low-density materials, not a rocky body like Earth. Remove the picture of Earth you are working with. The one below is the best fit to what the data actually shows. The designation is Hycean, a compound of hydrogen and ocean. The Hycean world category was proposed by Madhusudan's own research group in a 2021 paper in the Astrophysical Journal. A Hycean world has a thick hydrogen-dominated atmosphere sitting directly above a global liquid water ocean. No rocky surface accessible from the atmosphere. Below the hydrogen sky, pressure increases until conditions favour liquid water. The ocean could extend downward for hundreds or thousands of kilometres, with pressure and temperature increasing with depth until the water transitions to high-pressure ice at the base. The atmosphere-ocean interface experiences pressure conditions very different from Earth's ocean surface. Webb's observations provide 3 independent checks of the Hycean model. Methane and carbon dioxide are detected at concentrations consistent with a hydrogen-rich atmosphere in chemical equilibrium with a warm ocean beneath it. Ammonia is not detected. In a hydrogen-rich reducing atmosphere at K2-18b's temperature without an underlying ocean, thermodynamic equilibrium strongly predicts substantial ammonia. Its absence is consistent with an ocean surface absorbing atmospheric ammonia exactly as Earth's oceans do. 3 predictions of the Hycean model. 3 consistent results, not proof. But the model has passed multiple predictive tests, and that is how scientific models earn credibility. The host star K2-18 is an M2.5 dwarf with roughly 36% of the Sun's mass and about 4% of its luminosity. Red dwarfs are the most common type of star in the galaxy, accounting for approximately 70 to 75% of all stars by number. K2-18 B orbits at 0.14 astronomical units, closer than Mercury orbits our Sun. Because K2-18 is so much dimmer, K2-18b receives approximately 1.2 times Earth's solar flux, placing it near the inner edge of K2-18's habitable zone. K2-18b orbits its star once every 32.94 days. It is almost certainly tidally locked, the same face permanently toward the star, a permanent day side and a permanent night side, with atmospheric circulation redistributing heat between them. K2-18 is estimated to be approximately 2.4 billion years old. In 2.4 billion years on Earth, the first single-celled organisms with nuclei appeared. Multicellular life was still hundreds of millions of years in the future, and the atmosphere had begun its transformation from reducing to oxidizing. If life arose on K2-18b in the first billion years of its ocean's existence, as it did on Earth, the biosphere has had over 1 billion years to develop and establish the metabolic sophistication required to produce DMS as a routine byproduct. The potential biosphere on K2-18b, if it exists, would face a UV environment fundamentally different from Earth's ocean surface. K2-18 produces frequent flares, intense bursts of ultraviolet and X-ray radiation. On Earth, the ozone layer shields marine life from most UV radiation, but K2-18b's hydrogen atmosphere likely contains very little ozone. Life in K2-18b's ocean would need to contend with periodic UV spikes. The adaptation most available to it lies deeper in the water column, below the depth where UV penetrates, shielded by the water itself, which absorbs UV rapidly. DMS produced at depth would rise through the water column through mixing and upwelling, reaching the atmosphere above. The planet may be entirely ocean, not a poetic guess, the best fit to the data from the most capable infrared telescope humanity has ever built. What best fit does and doesn't mean is where the story gets more complicated than the headlines allow. You probably picture K218b as something like Earth, a rocky world with a recognizable atmosphere, orbiting a star at a habitable distance. The template your mind constructs from planet in the habitable zone is built from the only habitable planet you have ever experienced. K2-18b violates that template in nearly every meaningful way. The word Hycean combines hydrogen and ocean. A Hycean world, as Madhusudan's group defined it in a 2021 paper in the Astrophysical Journal, is a planet with a thick hydrogen-dominated atmosphere above a global liquid water ocean. No rocky surface accessible from the atmosphere. Below the hydrogen sky, pressure increases until conditions favour liquid water. The ocean could extend downward for hundreds or thousands of kilometres, with pressure and temperature increasing with depth until the water transitions to high-pressure ice at the base. Webb's observations provide several lines of evidence consistent with this structure. Methane and carbon dioxide are detected at concentrations fitting the Hycean model. In a hydrogen-rich atmosphere at K218b's temperature, if the atmosphere is in chemical equilibrium with a warm ocean beneath it, thermodynamic models predict abundant methane and moderate carbon dioxide. The ratio in the retrieved atmospheric composition is consistent with this prediction. More diagnostically, ammonia is not detected. In a hydrogen-rich atmosphere at K218b's temperature without an ocean, thermodynamic equilibrium strongly predicts substantial ammonia. Its absence is consistent with an ocean surface absorbing atmospheric ammonia, exactly as Earth's oceans do. The Hycean model makes specific predictions about what Webb should and shouldn't detect, and those predictive checks all passed. Methane abundance consistent with prediction, carbon dioxide consistent with prediction, ammonia absent as predicted. 3 independent checks of the model against the data are all consistent. The model has not been proven, but it has passed multiple predictive tests, which is how scientific models earn credibility. The question of whether K218b's ocean could support life given its specific environment is genuinely difficult to answer without direct sampling. Earth's ocean supports life across an enormous range of conditions. Hydrothermal vents on the deep ocean floor host dense communities at temperatures exceeding 100 degrees Celsius, under pressures hundreds of times atmospheric, in complete darkness, metabolizing sulfur compounds and hydrogen for energy rather than relying on photosynthesis. Psychrophilic organisms in polar seas survive near freezing. Halophiles in hypersaline lakes survive salt concentrations several times the ocean. If K218b's ocean has conditions within the range that extremophile organisms on Earth tolerate, the biological hypothesis is not constrained to require organisms similar to familiar marine life. Red dwarfs like K218 live far longer than Sun-like stars. K218, with 36% of the Sun's mass, will remain on the main sequence for approximately 30 to 40 billion years. If K218b has been in K218's habitable zone since the star formed roughly 2.4 billion years ago, the planet has had over 2 billion years of potentially habitable conditions. On Earth, life appeared within the first billion years of the planet having a stable liquid water ocean. A comparable head start for K218b is consistent with a mature biosphere, if life arose there at all. The planet may be entirely ocean. That is not a poetic guess. It's the best fit to the data from the most capable infrared telescope humanity has ever built. But best fit to the data is not the same as confirmed. The 99.7% contains a 0.3%, and understanding exactly what that 0.3% means is the part of this story that the headlines consistently fail to convey accurately. The question of phosphorus availability for life on K218b is worth examining. because phosphorus is often cited as a potentially limiting nutrient in astrobiology discussions. On Earth, phosphorus is delivered to the ocean primarily by the weathering of continental rocks and by hydrothermal venting from the seafloor. Phosphorus concentrations in the ocean are low relative to biological demand, making it a growth-limiting nutrient in many regions. If K2-18b lacks exposed rocky continents, which is what the Heysian model implies, the primary phosphorus source for the ocean would be hydrothermal venting from any rocky layer beneath the deep ocean. Whether this single source is sufficient to support a biosphere of the size implied by the DMS detection is genuinely uncertain. The energy source question is also worth considering. On Earth, most marine biology ultimately depends on photosynthesis as the primary energy input to the ecosystem. Under K2-18b's thick hydrogen atmosphere, visible light from K2-18 would be filtered and reduced in intensity before reaching the ocean's surface. If photosynthesis is limited, chemosynthesis using chemical energy from hydrothermal vents could support a biosphere in low-light conditions. Chemosynthetic organisms on Earth do not require sunlight. A biosphere based primarily on chemosynthesis could exist below the ocean's UV penetration depth. The biosphere would produce DMSP and DMS through the same biochemical pathways regardless of its energy source, releasing DMS to the ocean surface through mixing. The vertical structure of K2-18b's ocean matters for the biosphere hypothesis. On Earth, most marine DMS production is concentrated in the upper 200 meters of the ocean, where phytoplankton grow in the photic zone. If K2-18b's ocean is dimly lit at the surface, the photic zone may be shallow or absent, and the primary biology might be concentrated at hydrothermal vents in the deep ocean. DMS produced at depth would need to mix upward through the ocean water column to reach the atmospheric concentrations Webb observed. Whether ocean mixing rates on a Heysian world are sufficient to transport DMS from depth to the surface depends on the planet's tidal dissipation, internal heat flux, and the density stratification of the water column. The question of whether K2-18b's ocean would have access to the elements required for life, as we know it, is also important. Life on Earth requires carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the CHNOPS elements, along with trace metals. Carbon and hydrogen are abundant in K2-18b's atmosphere. If K2-18b has a rocky layer beneath its deep ocean, hydrothermal venting could deliver phosphorus and trace metals to the ocean water. Whether this delivery is adequate for a biosphere large enough to produce the observed DMS signal is a quantitative question that depends on the planet's internal structure and the efficiency of its geochemical cycles. The overall picture that emerges from assembling the constraints is one of a world that is strange by Earth standards, but not obviously incompatible with life by the broad standards set by extremophile biology on Earth. A hydrogen sky, a global ocean, a red dwarf star, tidal locking, periodic UV flares, no exposed rocky continents, and conditions that have persisted for over 2 billion years. Against these constraints, the biological hypothesis requires nothing that known biochemistry cannot support. It requires only that chemistry similar to what DMSP-producing organisms do on Earth happens on K2-18b as well, whether or not that chemistry is identical at the molecular level. The planetary age also matters for the biological hypothesis. K2-18 is estimated to be approximately 2.4 billion years old based on stellar evolution models. If life arose on K2-18b in the first billion years of its ocean's existence, consistent with how quickly life appeared on Earth, the biosphere has had over 1 billion years to develop. That is sufficient time to develop the metabolic sophistication required to produce DMS as a metabolic byproduct at the scale implied by the Webb detection. A mature biosphere of 1 to 2 billion years of age is consistent with the signal strength observed. What 3 sigma does not promise. Your brain treats 99.7% as near certainty, because evolutionary pressure shaped you to act on probabilities well below that. If there was a 99.7% chance that a sound in the undergrowth was a predator, your ancestor who treated it as certain lived longer than the one who weighed the 0.3%. You're not equipped to intuitively feel the difference between 99.7% and 99.9997%. Both feel like, sure. Only one of them is the scientific standard for announcing a particle physics discovery. In particle physics, 99.7% is not enough to publish a discovery. The field of high-energy physics uses a 5 sigma standard for discovery announcements, corresponding to a false alarm probability of roughly 1 in 3.5 million. This standard exists because of history. The history of particle physics contains a documented pattern of 3 sigma signals that turned out to be statistical fluctuations. Multiple 3 sigma anomalies in the 1980s and 1990s failed to survive additional data collection. The 5 sigma standard was adopted after the community learned repeatedly that 3 sigma was insufficient. When the ATLAS and CMS detectors reached 3.6 and 3.8 sigma respectively on the Higgs boson, in December 2011, the community treated it as credible but not confirmed. 7 months later, 5 sigma. The Higgs was real. 3 sigma means you're probably right. It also has a name for when you're not: a false alarm. There is also the multiple comparisons problem. Atmospheric retrievals test not a single hypothesis, but a broad library of molecular combinations. When you test many molecules simultaneously and report the one returning the highest significance, the effective false alarm rate for that winning molecule is higher than its nominal significance suggests. This is the look elsewhere effect. Madhusudan's team applied corrections for multiple comparisons. The 99.7% survived those corrections, but different independent groups applying the correction differently have found adjusted confidence levels ranging from approximately 2.7 to 3.1 sigma. All still strong by most scientific standards. None strong enough to call a confirmed discovery by the most stringent criteria. A system at 99.7% reliability sounds robust. Run that system 370 times, and you expect 1 false positive. Atmospheric retrievals test hundreds of molecular combinations across multiple wavelength ranges. The effective number of independent tests is not 1. The 0.27% false alarm rate applies to a single clean comparison. The real false alarm rate accounting for the breadth of the retrieval is higher. How much higher depends on methodological choices that reasonable scientists disagree about. That's not a flaw in the science. That is the honest description of where the evidence sits. The broader context. Exoplanet atmospheric science has calibrated its treatment of 3 sigma results from Hubble-era experience, not from particle physics standards. The first detection of water vapor in K218b's atmosphere, made with Hubble in 2019, was reported at 3 sigma and treated as a significant discovery. The Webb era brought a large improvement in sensitivity. In the context of the field's historical standards, a 3 sigma Webb detection is considered highly significant. In the context of particle physics standards, it is considered preliminary. K2-18b sits at the intersection of these 2 scientific cultures, and different researchers apply different standards depending on their background. Neither perspective is wrong. They are applying different discipline-specific standards to the same number. Second rung of the ladder. You think, fine, 3 sigma is not 5 sigma, but it's still strong, and the abiotic alternative has no mechanism. So the case is solid even if not confirmed. Then the question of what 5 sigma would actually require enters the picture, and the ladder shifts again. What does 99.7% actually describe in this context? It describes the confidence, under the team-specific data reduction pipeline, their atmospheric retrieval code, and their statistical framework, that dimethyl sulfide is required to explain the observed transmission spectrum. It does not describe the probability that K2-18b hosts life. It describes one technically precise thing. And understanding exactly what that one thing is what separates a careful reading of this finding from an excited one. You probably read 99.7% and felt something close to certainty. That response is natural, and in many everyday contexts would be entirely appropriate. A drug approved at 99.7% confidence of efficacy would be trusted by physicians worldwide. A structural engineering analysis returned at 99.7% confidence would be acted on without hesitation. In ordinary life, 99.7% is as close to sure as consequential decisions ever require. In particle physics, 99.7% is not enough to call something real. 3 sigma means you are probably right. It also has a name for when you're not, a false alarm. In atmospheric spectroscopy of exoplanets, the statistical environment differs from particle physics. You're not counting discrete particle collision events against a precisely modelled background. You are comparing 2 continuous spectra, each with noise from photon counting statistics, stellar variability, instrument systematics, and data reduction pipeline choices. The concept of sigma translates across these domains, but not perfectly. A 3 sigma atmospheric detection does not carry exactly the same probabilistic weight as a 3 sigma particle detection. The broader context for this statistical discussion is the history of exoplanet atmospheric science over the previous decade. Before Webb, the primary instrument for transmission spectroscopy was the Hubble Space Telescope. Hubble spectra had lower signal-to-noise and narrower wavelength coverage than Webb. The exoplanet atmospheric science community calibrated its treatment of 3 sigma results from Hubble-era experience rather than from particle physics standards. The first detection of water vapor in K2-18b's atmosphere was made with Hubble in 2019 at 3 sigma, and it was treated as a significant discovery. The Webb era brought a large improvement in sensitivity. In the context of the field's historical standards, a 3 sigma Webb detection is considered highly significant. In the context of particle physics standards, it is considered preliminary. K2-18b sits at the intersection of these 2 cultures, and different researchers apply different standards depending on their background. Independent reanalysis has produced a range of results. Multiple groups have applied different retrieval frameworks to the publicly available K2-18b transit data. Results range from consistent with the original 99.7% to confidence levels somewhat below 3 sigma, depending on pipeline choices. No published independent reanalysis has returned a confident non-detection. The signal is present across multiple analyses. The debate is about its strength, not its existence. So, what does 99.7% actually describe in this context? It describes the confidence level under the team's specific data reduction pipeline, their atmospheric retrieval code, and their statistical framework that dimethyl sulfide is required to explain the observed transmission spectrum. It does not describe the probability that K2-18b hosts life. It describes one technically precise thing, and understanding exactly what that one thing is what separates a careful reading of this finding from an excited one. The explanation that does not exist yet. The skeptical position on K2-18b is not that the signal is wrong. The skeptical position is that the photochemistry of hydrogen-dominated Hycean-type atmospheres has not been characterized in laboratory conditions sufficiently to rule out abiotic DMS production at the concentrations implied by the Webb detection. This is a legitimate scientific statement. It is held by serious researchers working in good faith, and it is, when examined carefully, a statement about an absence of laboratory data rather than a statement about a present alternative hypothesis. To demonstrate an abiotic alternative, you would need to simultaneously satisfy a sulfur-bearing feedstock molecule present in K218b's atmosphere at sufficient abundance, a photochemical or thermochemical reaction pathway converting that feedstock to dimethyl sulfide, a production rate fast enough to maintain atmospheric DMS concentrations at the levels consistent with the Webb detection, and a mechanism preventing the DMS from being destroyed by photolysis or oxidation faster than it is produced. Each of these conditions needs to be satisfied simultaneously. In a hydrogen-rich atmosphere at K218b's specific temperature and pressure profile, under K218's specific ultraviolet flux, none of the conditions is individually impossible. All four together, at the required rates, in an environment that has never been directly studied, have not been demonstrated. To explain away the signal without biology, you need chemistry. The universe has never demonstrated. Laboratory astrochemistry of Hessian atmospheric conditions is a genuinely young field. Before Madhusudan's group proposed the Hessian planet category in 2021, there was no strong motivation to run laboratory experiments simulating the specific atmospheric chemistry of hydrogen-dominated ocean worlds at K218b's temperature and pressure. Following the K218b detection, several laboratory groups began designing experiments specifically targeting DMS photochemistry in Hessian analog conditions. The timescale for this work is years. None of the published results as of this investigation had demonstrated abiotic DMS production at the required rates. The experiments are ongoing. The asymmetry of the evidence has a formal Bayesian expression. The biological explanation has a prior probability that is uncertain but non-zero. Life can produce DMS, so biological DMS production on K2-18b is not impossible a priori. The abiotic explanation has a prior probability that depends on whether a viable pathway at the required rate exists. If no such pathway has been demonstrated, the abiotic hypothesis carries a lower Bayesian prior. The likelihood of the observed signal given the biological hypothesis is high. The mechanism produces DMS at exactly the concentrations needed on Earth. The likelihood of the observed signal given the abiotic hypothesis is lower, because no abiotic mechanism has been shown to produce DMS at those concentrations. In informal Bayesian terms, the biological explanation is both more plausible a priori and more consistent with the observed data. One side has evidence, the other has a logical possibility. There is also an important asymmetry in what it would mean if the laboratory experiments succeed. If a future laboratory study demonstrated a viable abiotic DMS production pathway in Hessian atmospheric conditions at the concentrations required by the Webb detection, the biological interpretation of the K2-18b signal would be significantly weakened. The detection itself would still stand. What the detection means would have changed. The 99.7% would still describe a real signal. Its biosignature value would be reduced. This is the correct scientific outcome if the abiotic alternative is real. It's not the outcome so far. This is what productive scientific uncertainty looks like. A claim is made. The community identifies the weakest link in the evidence chain. Experiments are designed to test that link. Papers appear. The confidence level rises or falls. The K2-18b DMS detection is in the middle of this process, and the scientific community approved more telescope time to run the most direct available test. The skeptical position on K2-18b is not that the signal is wrong. Researchers who are cautious about this finding are not disputing that the transmission spectrum contains features consistent with dimethyl sulfide. They are making a more specific and technically defensible argument. The photochemistry of hydrogen-dominated Hycean-type atmospheres has not been characterized in laboratory conditions sufficiently to rule out abiotic DMS production at the concentrations implied by the Webb detection. This is a legitimate scientific statement. It is also, when examined carefully, a statement about an absence of laboratory data rather than a statement about a present alternative hypothesis. What would an abiotic explanation need to demonstrate? A specific photochemical or thermochemical pathway operating in the pressure and temperature conditions of K2-18b's atmosphere under K2-18's ultraviolet flux that produces DMS at rates sufficient to maintain atmospheric concentrations consistent with the Webb signal against the ongoing photolytic destruction of DMS by that same UV flux. Each condition needs to be simultaneously satisfied, and the production rate needs to reach the required level. The most plausible candidate pathway begins with hydrogen sulfide. In a reducing hydrogen-rich atmosphere, H2S can form through volcanism or through atmospheric chemistry involving sulfur-bearing compounds. H2S can react with methane under UV irradiation to produce methanethiol. Methanethiol can react with methyl radicals produced when methane is photolyzed in the upper atmosphere to yield DMS. The reactions are real. They have been demonstrated in laboratory conditions. The chemistry is not fabricated. The problem is the rate. Laboratory measurements of DMS production from the methanethiol pathway in reducing conditions, scaled to K2-18b's estimated atmospheric conditions and UV flux, produce steady-state atmospheric DMS concentrations between 1 and several orders of magnitude below what is needed to generate the Webb signal. An order of magnitude is a factor of 10. Several orders of magnitude is a factor of 1,000 or more. Bridging this gap would require either a faster mechanism not previously observed in any analog environment, or conditions in K2-18b's atmosphere substantially more favourable to this chemistry than anything studied to date. The laboratory astrochemistry of Hycean atmospheric conditions is a genuinely young field. Before Madhusudan's group proposed the Hycean planet category in 2021, there was no strong motivation to run laboratory experiments simulating the specific atmospheric chemistry of hydrogen-dominated ocean worlds at K2-18b's temperature and pressure. Following the K2-18b detection, several laboratory groups began designing experiments specifically targeting DMS photochemistry in Hycean analog conditions, using photochemical reactors with mixtures of hydrogen, methane, and hydrogen sulfide irradiated with M-dwarf UV spectra. The timescale for this work is years. None of the published results as of this investigation had demonstrated abiotic DMS production at the required rates. The asymmetry of the evidence has a formal statistical expression. In Bayesian reasoning, you compare hypotheses by multiplying their prior probabilities by their likelihoods given the evidence. The biological explanation has a prior probability that is uncertain, but non-zero. We know life can exist and can produce DMS, so biological DMS production on K2-18b is not a priori impossible. The abiotic explanation has a prior probability that depends on whether a viable pathway at the required rate exists. If no such pathway has been demonstrated, the abiotic hypothesis carries a lower Bayesian prior. The likelihood of the observed DMS signal given the biological hypothesis is high. The mechanism produces DMS at exactly the concentrations needed. The likelihood given the abiotic hypothesis is lower, because no abiotic mechanism has been shown to produce DMS at those concentrations. In informal Bayesian terms, the biological explanation is both more plausible a priori and more consistent with the observed data. The abiotic alternative is neither. There is a general principle in atmospheric science called disequilibrium biosignatures that is directly relevant to the DMS case. Earth's atmosphere is wildly out of chemical equilibrium. Oxygen and methane coexist at concentrations that are thermodynamically unstable. The fact that both persist at their observed levels is maintained only by continuous biological production of both. A planetary atmosphere far from chemical equilibrium implies some active process maintaining the disequilibrium, and biology is the most efficient candidate. DMS on K2-18b would be a disequilibrium biosignature. It cannot accumulate to detectable concentrations from abiotic chemistry at the required rate, so its presence implies an active production source. One aspect of the abiotic alternative that receives less attention than it deserves is the source of sulfur for the candidate abiotic DMS pathway. The pathway requires hydrogen sulfide as a feedstock. On K2-18b, H2S would need to be produced by volcanic outgassing from a rocky interior, if one exists below the deep ocean, or by atmospheric chemistry involving sulfur-bearing compounds delivered by meteorites or comets. The abundance of H2S in K2-18b's atmosphere is not directly constrained by the current NIR spec data, because H2S absorbs at wavelengths not covered at the signal-to-noise level of the current dataset. If the MIRI follow-up data provides a constraint on the H2S abundance, it would directly test whether enough feedstock is available for the abiotic pathway. There is also an important asymmetry in what would happen if the laboratory experiments succeed in demonstrating a viable abiotic DMS production pathway at the concentrations required by the Webb detection. The biological interpretation of the K2-18b signal would be significantly weakened. The detection itself would still stand, but its biosignature value would be reduced because an abiotic explanation would now exist. This is the correct scientific outcome if the abiotic alternative is real. It wouldn't mean the detection was fraudulent. It would mean the interpretation was revised in light of new evidence. The 99.7% would still describe a real signal. What the signal means would have changed. The laboratory astrochemistry of Hessian atmospheric conditions is a genuinely young field. Before Madhusudan's group proposed the Hessian planet category in 2021, there was no strong motivation to run laboratory experiments simulating the specific atmospheric chemistry of hydrogen-dominated ocean worlds at K2-18b's temperature and pressure conditions. Following the K2-18b detection, several laboratory groups began designing experiments specifically targeting DMS photochemistry in Hessian analog conditions, using photochemical reactors with mixtures of hydrogen, methane, and hydrogen sulfide irradiated with M-dwarf UV spectra. The timescale for this work is years. None of the published results as of this investigation had demonstrated abiotic DMS production at the required rates. The broader lesson of the abiotic situation for how to think about biosignature detection in general is worth stating explicitly. The absence of a demonstrated abiotic pathway is not the same as the presence of a confirmed biological source, but the asymmetry between a demonstrated mechanism with a confirmed track record and a placeholder hypothesis with no demonstrated mechanism is not neutral. In science, you work with the evidence you have. The evidence currently available supports the biological interpretation and does not support the abiotic alternative. That could change when the laboratory experiments produce results. If it does, the community will update accordingly. Until it changes, the most parsimonious interpretation of the evidence is the one that doesn't require the discovery of previously unknown chemistry. The asymmetry of the evidence has a formal statistical expression. In Bayesian reasoning, you compare hypotheses by multiplying their prior probabilities by their likelihoods given the evidence. The biological explanation has a prior probability that is uncertain but non-zero. Life can exist and can produce DMS, so biological DMS production on K2-18b is not impossible. If no abiotic pathway at the required rate has been demonstrated, the abiotic hypothesis carries a lower Bayesian prior. The likelihood of the observed signal given the biological hypothesis is high. The likelihood given the abiotic hypothesis is lower. In informal Bayesian terms, the biological explanation is both more plausible a priori and more consistent with the observed data. More time on the same sky. Time allocation committee decisions for the James Webb Space Telescope are among the most competitive resource allocation processes in contemporary science. The telescope operates on annual observing cycles. Research groups worldwide compete for hours on the mirror. In Cycle 1, there were 1,173 approved programs from a substantially larger pool of submissions, with oversubscription rates exceeding 5-to-1 in many high-priority fields. Getting additional Webb time on a target already observed in a previous cycle means persuading a peer review committee that the new observations will answer questions the existing data cannot resolve, and that those questions are important enough to justify the opportunity cost. Additional observing time for K218b was approved. The scientific case rested on a specific and testable prediction. The original NIR spec detection covered wavelengths from 0.97 to 5.27 micrometers. DMS has absorption features in this range, but not its strongest and most diagnostically distinctive feature, which falls near 9.5 micrometers in the mid-infrared. Webb's MIRI instrument covers wavelengths from roughly 5 to 28 micrometers, including the 9.5 micrometer range. The 9.5 micrometer DMS absorption feature occurs at a wavelength well separated from the primary absorption bands of other molecules likely present in K218b's atmosphere. If DMS is genuinely present, MIRI should detect absorption at 9.5 micrometers at a strength predictable from the NIR spec retrieval. If the NIRSpec signal was a systematic artifact or a misidentification, the MIRI data wouldn't show the expected absorption. NIRSpec and MIRI use different detector technologies, different optical paths within the telescope, and different calibration approaches. A systematic error affecting the NIRSpec data at 3.4 micrometers wouldn't in general produce a corresponding artifact in MIRI data at 9.5 micrometers. A DMS signal appearing consistently in both NIRSpec and MIRI at the predicted wavelengths and relative strengths would be extremely difficult to explain as an artifact of either instrument alone. This is the essential logic of the multi-wavelength test. Detection at multiple wavelengths with different instruments provides a much stronger case than any single instrument detection at any confidence level. Multiple K218b transits were scheduled across Webb's Cycle 2 and Cycle 3 observing programs. K218b transits its star every 32.94 days, providing approximately 11 transit opportunities per year. Each MIRI transit observation requires several hours of telescope time, including pre-transit and post-transit baseline measurements for calibration. The approved program allocated enough transit observations to accumulate the photon statistics needed to detect or robustly rule out the predicted 9.5 micrometer DMS feature. The follow-up observations were approved. The results have not been fully published. That silence is its own kind of answer. Null results in high-profile scientific disputes are published quickly. If the MIRI data had cleanly shown no absorption at 9.5 micrometers, contradicting the NIRSpec DMS identification, a paper would have appeared promptly. A null result contradicting a high-profile claim at 3 sigma is highly publishable. The kind of result the community has a strong interest in knowing quickly. The absence of such a refutation paper suggests the MIRI data didn't cleanly contradict the NIR spec detection. Conference presentations from researchers working with the extended dataset given at major astronomy meetings in 2024 and early 2025 indicated that the DMS signal remained consistent across the additional observations. The 9.5 micrometer MIRI data showed features consistent with the DMS identification from NAR spec. Whether the combined dataset had reached 4 sigma or 5 sigma was not announced at the conference stage, because those numbers require completed peer-reviewed analysis. An independent reanalysis published as a preprint in 2024 found the DMS detection statistically present at approximately 2.7 sigma, somewhat below the original 99.7%, and noted that the MIRI follow-up would be decisive. The additional transits observed in the follow-up program are not simply repeating the same observation. Each transit provides new data because the instrument calibration evolves over time. The specific detector geometry and pointing vary slightly between observations taken months apart, and any time-variable systematic errors that affect one observation are less likely to affect all observations taken at different epochs. If the DMS signal survives a stack of several transits taken over more than a year, the probability that it's a time-variable instrumental artifact is significantly lower than if it only appeared in transits taken in rapid succession. The follow-up observations were approved. The data was collected. The signal was not refuted. If the evidence so far has you subscribe, there is more coming from K218b, and this channel will cover it as it arrives. Now consider what 5 sigma confirmation would actually mean for the universe as we understand it. The MIRI instrument uses an arsenic-doped silicon detector array, cooled to 6.7 Kelvin by an active closed-cycle cryocooler. At this temperature, the detector can measure photons at mid-infrared wavelengths with very low dark current. The mid-infrared wavelength range MIRI covers is valuable for atmospheric characterization because it includes both the transmission spectrum of the atmospheric limb during transit and the thermal emission spectrum of the planet's night side during secondary eclipse. For K218b, the MIRI transit observations provide the transmission signal at 9.5 micrometers. MIRI can also potentially constrain the temperature profile of the atmosphere and cloud structure through secondary eclipse measurements, providing additional context for interpreting the transmission spectrum DMS detection. The approval of the follow-up program sent a signal through the scientific community about how the K218b DMS detection was being treated institutionally. Time allocation committees are composed of senior scientists representing the community. When such a committee approves significant additional time for a follow-up program based on a 3 sigma detection, it's a statement that the 3 sigma detection is scientifically credible enough to warrant the investment. The scientific community represented by the committee found the K218b DMS signal credible enough to act on. The peer review process for the follow-up publication will be particularly thorough given the context. The K218b DMS detection was under intense community scrutiny before the follow-up data was collected. The independent reanalyses, the preprints, and the conference presentations have set a high bar for what the follow-up publication needs to demonstrate. Referees reviewing the follow-up paper will specifically evaluate whether the MIRI data shows the predicted 9.5 micrometer feature, whether the extended NIR spec dataset raises the confidence level as expected for a genuine signal, and whether the combined dataset addresses the methodological concerns raised by independent groups. The follow-up paper will be the most carefully scrutinized paper in this field in years. The approval of the follow-up program also sent an institutional signal through the scientific community. Time allocation committees are composed of senior scientists representing the broader research community. When such a committee approves significant additional telescope time for a follow-up program based on a 3 sigma detection, it's a statement that the detection is scientifically credible enough to warrant the investment of additional scarce resources. The committee is not endorsing the biological interpretation. It is endorsing the scientific priority of testing the detection with the most definitive available follow-up observation. That endorsement is itself evidence about how the K218b DMS signal is being treated institutionally. The MIRI instrument presents its own technical challenges for this observation. MIRI detects light at wavelengths from approximately 5 to 28 micrometers. At these wavelengths, the telescope's own thermal emission becomes a significant source of noise if the telescope is not cold enough. Webb minimizes this by cooling the MIRI detector assembly to just 6.7 Kelvin by an active cryocooler. Even at this temperature, MIRI observations of faint atmospheric features require careful modeling and subtraction of the background. The integration time required to detect a DMS feature at K218b's distance with MIRI is longer per transit than for NER-spec observations, because the 9.5 micrometer DMS feature falls in a wavelength region where instrument sensitivity is lower and background noise is higher. What makes the MIRI test particularly definitive is the complementarity of the two instruments. NER-spec and MIRI use different detector technologies, different optical paths within the telescope, and different calibration approaches. A systematic error affecting the NER-spec data would not in general produce a corresponding artifact in MIRI data at a completely different wavelength range. The two instruments sample different portions of the electromagnetic spectrum with different hardware. A DMS signal appearing consistently in both NIR-spec and MIRI at the predicted wavelengths and relative strengths would be extremely difficult to explain as an artifact of either instrument alone. An independent reanalysis published as a preprint in 2024 found the DMS detection statistically present at approximately 2.7 sigma, somewhat below the original 99.7%, and noted that the MIRI follow-up would be decisive for establishing whether the near-infrared detection reflected genuine DMS or a partial misidentification. That preprint is consistent with the signal being genuine, but also consistent with it being near the edge of detectability with the original dataset alone. The MIRI test resolves this ambiguity in a way that additional NIR-spec data alone cannot. It tests the molecular identity of the absorber, not just its presence at one wavelength range. The scientific community approved more time on this target. The data from that time was collected. The signal was not refuted. What would confirmation of the MIRI prediction mean in practical terms? It would mean the DMS detection had survived its strongest available test. The confidence level would increase substantially. The case against systematic artifact as the explanation would be much stronger. The community would begin treating the DMS detection as highly probable rather than merely credible. Independent groups would rush to reanalyze the combined dataset. The publication of a result approaching or exceeding 5 sigma would generate a response from the community that the original announcement could not claim. What the universe looks like. After that, suppose the extended dataset reaches 5 sigma. Suppose the peer-reviewed publication arrives with MIRI confirmation and independent reanalysis agreement. What does the scientific landscape look like the morning after? The first implication is statistical and the most consequential. A confirmed biosignature on K218b would mean life arose independently in at least 2 places in the observable universe, Earth and K218b. The distance between them is 124 light-years. In our galaxy, 100,000 light-years across, this is a local distance. The sphere of space within 124 light-years of Earth contains roughly 1,000 star systems. If 2 of those independently produced life, a rough Bayesian estimate places FL, the Drake equation's term for the fraction of habitable planets where life develops, at a minimum of several tenths of a percent. The entire uncertainty range collapses. Life is not extraordinarily rare. Life is common. That single conclusion changes every calculation in astrobiology. One confirmed biosignature doesn't mean neighbours. It means life is not the exception. That changes everything. If you compress Earth's 4.5 billion years of history into a single calendar year, simple cells appear in March, complex cells appear in July, complex multicellular life appears in mid-November, modern humans appear in the last 10 minutes of December 31st, radio broadcasting began in the last 0.0004 seconds. The communicative phase of civilization, the window during which we are detectable and listening, is not even visible in the compressed timeline unless you use a microscope. A K2-18b biosignature would confirm that life is widespread, while explaining absolutely nothing about why the universe appears electromagnetically silent. Both civilizations would be there. Both would be invisible to each other. The Fermi paradox doesn't dissolve, it sharpens. A confirmation would directly refute the rare Earth hypothesis in its strongest form. The rare Earth hypothesis proposes that the combination of factors making Earth habitable, a large moon stabilizing axial tilt, Jupiter as a gravitational shield, plate tectonics recycling carbon, a specific stellar spectral type, is so improbable that Earth-like life-bearing planets are vanishingly rare. K2-18b has none of these features. It's a tidally locked Hycean world orbiting a red dwarf with no evidence of a stabilizing moon, no equivalent of Jupiter shielding it, no exposed rocky continents, and a star utterly different from the Sun. If life arose there, it means life doesn't require any of the factors the rare Earth hypothesis treats as prerequisites. The template for life expands. K2-18b orbits a red dwarf. Red dwarfs comprise roughly 70 to 75% of all stars in the galaxy. Sub-Neptune planets, K2-18b's size class, are the most commonly detected planetary size class in Kepler survey data. If Hycean worlds around red dwarfs can host life, the fraction of the galaxy's real estate qualifying as potentially habitable is far larger than Earth-centric calculations suggested. Estimates that produce tens of billions of potentially habitable Earth-analog planets in the Milky Way may need to be revised substantially upward. Red dwarfs also live far longer than Sun-like stars. K2-18 will remain on the main sequence for roughly 30 to 40 billion years. Hycean worlds around red dwarfs could remain habitable for timescales that dwarf the current age of the universe. The survey implications follow directly. If K2-18b's DMS detection is confirmed, the appropriate scientific response is to survey the other known Hycean worlds and sub-Neptune planets for DMS and other biosignature gases. There are dozens of known planets in the sub-Neptune size range with orbital parameters and stellar environments broadly similar to K2-18b. Webb is capable of measuring transmission spectra for the best targets among these. A systematic survey that finds DMS in multiple Hycean worlds would suggest life is common in this planetary environment. Finding DMS only in K2-18b would be more consistent with K2-18b having unusual properties. Either result would be informative. None of this matters in any practical sense if you can't get there, and understanding what 124 light-years forecloses is the part of this story that the excitement around the 99.7% consistently leaves out. There is a philosophical dimension to this statistical implication worth making explicit. If life can only arise through an extraordinarily unlikely sequence of events, finding two examples within 124 light-years of each other would be an astonishing coincidence. The probability of this coincidence, given a very low frequency of life, would itself be very low. Finding a second example in the local neighborhood pushes strongly against the low-frequency model, because coincidences this extreme are more readily explained by life being common than by life being rare. A K2-18b confirmation would eliminate one of the most comfortable resolutions to the question of whether life is rare. The second implication is about the template for life. K2-18b is not Earth. Its atmosphere is hydrogen and helium, not nitrogen and oxygen. Its ocean, if it has one, exists beneath a hydrogen sky with pressure and chemistry, unlike Earth's ocean surface. If life arose there, it means the origin of life doesn't require oxygen, a rocky surface, a sun-like star, or any of the specific conditions that characterize Earth. The set of conditions under which life can originate is broader than Earth alone indicated. Let us take this to the limit. K218b orbits a red dwarf. Red dwarfs comprise roughly 70 to 75% of all stars in the galaxy. Sub-Neptune planets are the most commonly observed planetary size class in Kepler survey data. If Hycean worlds around red dwarfs can host life, the fraction of the galaxy's real estate qualifying as potentially habitable is far larger than Earth-centric calculations suggested. Red dwarfs also live for tens of billions of years. If life can arise on a Hycean world around a red dwarf, those worlds will remain habitable for timescales that dwarf the current age of the universe. Life would not just be common now, it would become increasingly common over cosmic time, on worlds orbiting stars that will outlast everything we currently recognize as part of the cosmos. A confirmed K218b biosignature would also sharpen the Fermi paradox specifically. One resolution of the paradox is that life itself is so rare that intelligent life is vanishingly improbable. A confirmed biosignature eliminates that resolution. If marine microbes exist on K218b, the question becomes not, why is there no life? But, why? Given that there is life, is there apparently no detectable intelligence? That is a harder question with no comfortable answers. None of this matters in any practical sense if you can't get there. And what 124 light-years forecloses is the part of this story that the excitement around the 99.7% consistently leaves out. The implication of K2-18b, confirmation for how future biosignature searches are designed, is significant regardless of the ultimate resolution. Before K218b, the primary focus of biosignature search strategy was on Earth-analog planets orbiting sun-like stars. The Habitable Worlds Observatory, a next-generation space telescope in early planning stages at NASA, was designed primarily with the goal of directly imaging Earth-analog planets in the habitable zones of nearby sun-like stars. K218b demonstrates that Hycean worlds around red dwarfs may be equally or more accessible for biosignature detection, and that they may be more common. A confirmation of K218b would likely drive a reassessment of survey strategy for future biosignature missions. There is a specific version of the Fermi paradox that a K218b biosignature confirmation would sharpen most directly. The rare Earth hypothesis proposes that the combination of factors that made Earth habitable is so improbable that Earth-like life-bearing planets are vanishingly rare in the galaxy. A confirmed biosignature on K218b, a tidally locked Hycean world orbiting a red dwarf, with none of the features the rare Earth hypothesis emphasizes, would directly refute the hypothesis in its strongest form. It would demonstrate that life doesn't require a large stabilizing moon, does not require a giant planet gravitational shield, does not require plate tectonics, and does not require a sun-like star. The question of whether K218b's hypothetical biosphere has had time to evolve toward anything resembling biological complexity is a separate and currently unanswerable question. K2-18b is roughly 2.4 billion years old. If life arose there in the first billion years, the biosphere would currently be at a developmental stage roughly equivalent to Earth, roughly 1.4 billion years ago. Potentially photosynthetic single-celled life in an ocean, producing metabolic byproducts like DMS, but nothing resembling complexity in the sense of multicellular organization. The DMS signal from K218b is potentially telling us about the most ancient and simple form of biology: single-celled organisms doing chemistry in an ocean. There is also an astrobiological implication for the concept of a biosphere's atmospheric footprint. K218b's biosphere, if it exists, is detectable at 124 light-years by a telescope in operation for less than 2 years. Earth's biosphere became detectable through oxygen absorption features roughly 2.4 billion years ago. K218b's biosphere, if it exists, is detectable not because it has transformed the planet's bulk, atmospheric composition, but because it produces a specific trace molecule at concentrations above the abiotic background. This implies that a biosphere does not need to be large enough to globally transform a planet's atmosphere to be detectable. A productive biosphere producing the right trace gas, one with no abiotic background, could be detectable without waiting billions of years. There is also a philosophical dimension to the statistical implication of 2 life-bearing planets in the same galactic neighborhood. If life can only arise through an extraordinarily unlikely sequence of events, finding 2 examples within 124 light-years of each other would be a striking coincidence. The probability of this coincidence, given a very low frequency of life, would itself be very low. Finding a second example in the local neighborhood pushes strongly against the low-frequency model, because coincidences this extreme are more readily explained by life being common than by life being rare. The Drake equations term the fraction of habitable planets where life develops is completely unconstrained by Earth alone. It could be close to 1, meaning life develops readily, or close to 0, meaning life is extraordinarily rare even when conditions allow. These scenarios are indistinguishable from a sample of 1. K218b would provide a second data point from approximately 1,000 star systems in the relevant volume of space. 2 life-bearing planets out of roughly 1,000 star systems implies an FL value of at minimum several tenths of a percent. That is a very different universe than the one where Earth might be the only example. The distance that makes none of this matter. Light travels at 186,282 miles per second. In 1 year, it covers approximately 5.88 trillion miles. In 124 years, it covers approximately 730 trillion miles. That is the distance to K218b. The number is too large to feel. So let us build the scale from something you can hold in your mind. If you represent the Earth as a basketball, roughly 24 centimeters across, the Moon sits approximately 7 meters away. The Sun is 26 meters away, across the room. Mars, at closest approach, is about 1.5 kilometers away. Jupiter is nearly 14 kilometers away. Neptune, the outermost planet, is over 800 kilometers away, roughly the distance from New York to Chicago. That is the solar system you were shown in school. Now, Alpha Centauri, the nearest star system on this basketball Earth scale, is 6.8 million kilometers away. That is roughly 18 times the actual distance from Earth to the Moon. K218b at 124 light-years is on this same basketball scale approximately 200 million kilometers away, more than the real distance from Earth to the Sun. On a scale where Earth is a basketball, K218b is farther away than our actual Sun. Walk that model. Start at the basketball Earth. Walk 26 meters to reach the basketball Sun. Keep walking past Neptune, 800 kilometers to reach the outer solar system. Now, walk toward K2-18b. Keep walking. By the time you have covered 200 million kilometers, you're still only at a basketball representing K2-18b. The solar system you knew fits inside a single room on this scale. The nearest star sits millions of kilometers away on this scale. K2-18b is 200 million kilometers away on this scale. You have not walked it. You have merely named it. The fastest human-made object ever built is the Parker Solar Probe during its closest solar passes, reaching approximately 394,000 miles per hour relative to the Sun. At 394,000 miles per hour, the travel time to K218b would be approximately 212,000 years. In 212,000 years on Earth, modern humans didn't yet exist for most of that span. Homo sapiens has been anatomically modern for roughly 300,000 years. A Parker Solar Probe launched today at the fastest speed any human-made object has ever achieved would arrive at K2-18b, when our species has lived approximately 70% of the time it has so far existed. The probe would arrive. The civilization that launched it would be unrecognizable or gone. Even a hypothetical spacecraft traveling at 1% of the speed of light, roughly 6.7 million miles per hour, vastly beyond any current or near-future propulsion technology, would take 12,400 years to reach K218b. In 12,400 years, the city of Jericho was founded, the pyramids of Giza were built, the Roman Empire rose and fell, the Renaissance happened, the Industrial Revolution happened, the nuclear age arrived, the internet was invented. All of human civilization, from its earliest permanent settlements to this moment, fits inside 12,400 years. A spacecraft launched at 1% light speed wouldn't arrive at K218b until after a travel time equal to all of recorded human history. If they exist and they are watching us right now, they are seeing Earth as it was in 1901. The light carrying information about Earth's current state, its atmospheric composition, its electromagnetic emissions, is currently 124 light-years away from K218b, en route, not yet arrived. What K218b's hypothetical observers would be detecting right now is the Earth before powered flight, before nuclear physics, before the transistor, before the internet, before we launched a single satellite. If they exist and they are watching, they don't yet know we can communicate deliberately with the cosmos. And whatever we send them today arrives in 2149. The barriers stack independently. Spatial distance, 124 light-years. Signal round-trip time, 248 years. Temporal existence window. Both civilizations must be in their communicative phase simultaneously. Given the compressed timeline of civilization, the probability of temporal overlap is uncertain at best. Energy cost. Broadcasting an omnidirectional radio signal detectable at 124 light-years requires power outputs we have never achieved and cannot sustain. Frequency alignment. We must broadcast and listen on the same frequency by coincidence. Directional alignment. A directed beam aimed in precisely misses the target by astronomical margins. Going electromagnetically dark. Advanced civilizations may cease detectable broadcasting. Each barrier is independent. Each is individually significant. Together they do not add, they multiply. What the 99.7% tells us, if it holds, is that something is alive on K2-18b, or was alive 124 years ago when the light Webb analyzed left the planet's atmosphere. We cannot distinguish alive now from alive then, because we receive only the light that left then. We can't visit. We cannot probe. We can't send a communicable signal and receive a response in any individual lifetime. We can observe additional transits. We can refine our understanding of the atmospheric composition. That is the complete list of things we can do. The discovery and the permanent isolation arrive at the same moment. You probably assume that confirming life on K2-18b would begin a new chapter in humanity's relationship with that world. More detailed observation, eventually some form of contact or study. The discovery as prologue. This assumption contains an error about scale so fundamental that correcting it requires rebuilding the relevant numbers from the ground. Start building the scale from something holdable. The distance from Earth to the Moon is approximately 240,000 miles. Light crosses it in about 1.3 seconds. Earth to Mars at closest approach is roughly 34 million miles, about 3 minutes for light. Earth to the Sun is 93 million miles, about 8 minutes. Alpha Centauri, the nearest star system, is approximately 25 trillion miles. Light takes 4.24 years. K2-18b is 730 trillion miles. Light takes 124 years. K2-18b is approximately 29 times farther than the nearest star. Even a hypothetical spacecraft travelling at 1% of the speed of light, roughly 6.7 million miles per hour, vastly beyond any current or near-future propulsion technology, would take 12,400 years to reach K2-18b. The city of Jericho has been continuously inhabited for approximately 11,000 years. A spacecraft launched at 1% light speed would not arrive until after a travel time longer than all of human civilization from its earliest permanent settlements. The communication constraint imposed by 124 light-years is worth exploring in both directions. In the direction from Earth to K2-18b, any signal sent today at light speed arrives in 124 years in approximately 2148. Any response arrives in 2272. The entire exchange, one question and one answer, takes 248 years, longer than the United States has existed as a nation. A question asked today would be answered, if answered, in a world transformed beyond recognition from our own. In the direction from K2-18b to Earth, if life on K2-18b is sophisticated enough to detect Earth's electromagnetic signatures, they're currently receiving signals from Earth as it was in 1901, before powered flight, before nuclear physics, before the transistor, before we launched a single satellite. If they're watching, they don't yet know we can communicate deliberately with the cosmos. The physics of the distance clarifies what it does and does not foreclose. It does not foreclose observation. Webb and its successors can continue observing K2-18b, extracting more information from each transit. What 124 light-years forecloses is physical access. Every mode of interacting with K2-18b that requires sending something there is foreclosed on any timescale relevant to current civilization. We can observe additional transits. We can refine our understanding of the atmospheric composition. We can increase the confidence level from 99.7% to higher. That is the complete list of things we can do. If they exist and they're watching us right now, they are seeing Earth as it was in 1901. What the 99.7% tells us, if it holds, is that something is alive on K2-18b as of 124 years ago. We cannot distinguish alive now from alive then, because we receive only the light that left then. We can't visit. We cannot probe. The discovery and the permanent isolation arrive in the same moment. There is a thought experiment worth walking through that clarifies the practical meaning of the distance. Suppose that tomorrow, the peer-reviewed confirmation paper appears with 5 sigma confidence and MIRI validation, and the scientific community unambiguously accepts that marine biology exists in K2-18b's ocean. What can you do with this knowledge that you could not do yesterday? You can observe K2-18b more carefully. You can plan more detailed spectroscopic observations with Webb and with future telescopes. You can use K2-18b as a calibration point for models of how life affects planetary atmospheres. You can update estimates of the frequency of life in the galaxy. You can survey other Hycean worlds with more urgency. All of this is real and scientifically valuable. What you can't do is any of the things science fiction has prepared you to expect. You can't send a message with any expectation of a reply in your lifetime. You can't send a probe with any expectation of it arriving in any lifetime you can intuitively imagine. You can't ask what the organisms look like, what their biochemistry is in detail, whether they have evolved toward complexity, or whether they have any awareness of their environment. All of these questions remain permanently behind a wall of distance that no physical object can cross faster than light. The confirmation would be a discovery with no practical consequence beyond Earth, and with the most profound theoretical consequence in human history simultaneously. What the distance to K218b means for the biology question is specific in an important way. Even if we confirmed with certainty that K218b hosts marine microbes, we could not study those microbes directly. We could not take samples, we could not culture them, we could not sequence their genomes, we could not determine whether they use DNA or an alternative information polymer. We could not determine whether they share a common ancestor with Earth life or arose independently. These are the questions that would most directly test whether life has a universal biochemistry or whether it takes different forms in different environments. We will never have direct access. The 124 light-years forecloses not just physical visits, but the entire domain of comparative biochemistry between K2-18b life and Earth life. The communication constraint imposed by 124 light-years is worth exploring in both directions. In the direction from Earth to K2-18b, any signal sent today at light speed arrives in 124 years in approximately 2148. Any response arrives in 2272. The entire exchange, one question and one answer, takes 248 years, longer than the United States has existed as a nation. In the direction from K2-18b to Earth, if life on K2-18b is sophisticated enough to detect Earth's electromagnetic signatures, they're currently receiving signals from Earth as it was in 1901, before powered flight, before nuclear physics, before we launched a single satellite. The nearest confirmed biosignature candidates beyond K2-18b, if future surveys find them, will almost certainly be at comparable or greater distances. The statistical expectation for the nearest inhabited world, even under optimistic assumptions about the frequency of life, is tens to hundreds of light-years. Every biosignature detection in human history will be behind a distance barrier measured in centuries or millennia of travel time at any speed currently achievable. The universe has built isolation into the architecture of star systems. There is no propulsion advance that changes this on any timeline that would be recognizable as human history. The physics of the distance clarifies what it does and does not foreclose. It does not foreclose observation. Webb and its successors can continue observing K2-18b, extracting more information from each transit. It does not foreclose theoretical understanding. What 124 light-years forecloses is physical access. Every mode of interacting with K2-18b that requires sending something there is foreclosed on any timescale relevant to current civilization. We can observe additional transits. We can refine our understanding of the atmospheric composition. We can increase the confidence level from 99.7% to higher. That is the complete list of things we can do. What confirmation of life on K2-18b would change, even though it changes nothing about the distance, is the framing of every future night you spend looking up. The stars were always there. The distances were always the same. The physics was always what it is. What would change is whether the lights you see in the sky are windows into a universe where life happens on one world in an otherwise empty cosmos, or windows into a universe where life is a normal feature of the right conditions wherever those conditions arise. Those are two profoundly different universes to live in, even if you can't visit either of them, the honest state of 99.7%. Let us strip every layer simultaneously, not the press release version, which prioritized caution, not the headline version, which prioritized impact. The actual evidence in the most precise language available. Webb observed K2-18b during two transit events using near-spec, covering wavelengths from 0.97 to 5.27 micrometers. Atmospheric retrieval analysis returned detections of carbon dioxide, methane, and dimethyl sulfide. The DMS detection confidence level was 99.7% under the team's statistical framework, 3 sigma. The paper appeared in the Astrophysical Journal Letters in September 2023 and passed peer review. The lead author is Niku Madhusudan at the University of Cambridge, one of the most respected atmospheric retrieval scientists in the field. No confirmed non-biological source for DMS at the concentrations implied by the detection has been demonstrated in any laboratory or observational analog environment. The best candidate abiotic pathway falls between 1 and several orders of magnitude below the required production rate. The biological mechanism is well characterized and operates at exactly the required rates on Earth. The biological explanation requires no new chemistry. K218b's atmospheric composition is consistent with a Hycean world. Thick hydrogen atmosphere, possible global liquid water ocean, habitable zone location, methane and carbon dioxide at Hycean predicted levels, ammonia absent as Hycean models predict. These features do not confirm a Hycean structure, but they are consistent with one, and they provide a plausible environment for the kind of marine biology that produces DMS on Earth. The case has gotten stronger with every observation. It has not yet crossed the line. That line is the whole question. MIRI follow-up observations were approved and conducted. Multiple transit events were observed across Webb's Cycle 2 and 3 programs. The DMS signal has not disappeared in the additional observations. Conference presentations in 2024 and early 2025 indicated the 9.5 micrometer MIRI data is consistent with the NeoSpec DMS identification. No refutation papers appeared. Full peer-reviewed results are in preparation. Independent reanalysis has found the signal present across multiple analyses at varying confidence levels, with no published study returning a confident non-detection. The path to 5 sigma involves specific predictable milestones. The extended and near-spec dataset should raise the near-spec-only confidence level toward or past 4 sigma if the signal is real, because signal-to-noise scales as the square root of the number of observations. Adding additional transits to the original 2 would push a genuine 3 sigma signal toward 3.5 to 4 sigma. The MIRI results, if they show the predicted 9.5 micrometer absorption, add an independent line of evidence that is qualitatively stronger than more of the same data. A genuine biosignature appearing in 2 different wavelength ranges with 2 different instruments is a different category of claim than the same biosignature appearing in more observations with the same instrument. If the combined dataset does not reach 5 sigma, that outcome is also scientifically informative. A signal that saturates at 3 to 4 sigma despite additional observations would be a warning sign that the signal is a systematic artifact. Systematic artifacts tend to appear at consistent confidence levels regardless of how much data is collected, because they are limited by the systematic error flaw rather than by photon counting statistics. A genuine molecular detection should grow in significance as more transits are observed. If the K2-18 BDMS signal fails to grow as expected, the community would significantly revise downward its confidence. Either outcome will be published, either outcome will be honest. What you're left holding, if you read all of this carefully, a 3 sigma signal of a molecule that only life produces at scale, in the atmosphere of a world with conditions plausible for that life, that has not disappeared under scrutiny, where the abiotic alternative has no demonstrated mechanism, and where the follow-up data is consistent with the original detection. Not proof. The strongest atmospheric biosignature candidate in the history of astronomy. Whether that case becomes a confirmed discovery depends on data that has been collected and is currently under analysis. The answer exists. It has not yet been published. 99.7% is where this story stands, not where it ends. The official statement used the word tentative. That word appeared in every headline that followed the paper. It was accurate. What was also accurate in the same paper, in the same data, was 99.7%. Both of those things were describing the same number. Two described the interpretation. One described the signal. The signal was not tentative. The source of the signal is. What 99.7% describes is the confidence level of a detection of a molecule that only one known process produces at scale, in the atmosphere of a world with conditions that process could plausibly operate in, where no competing explanation has been demonstrated. The number is attached to the signal. The signal is attached to the molecule. The molecule is attached to the only explanation that works. The chain is not broken. It has one link that has not been confirmed. That link is the source. There is a planet 124 light-years from here. Whatever is in its atmosphere has been exhaling something into a hydrogen sky for a span of time that probably exceeds 1 billion years. The light from its last transit carries the record of those exhalations, encoded as absences at specific infrared wavelengths, and that light has travelled 730 trillion miles to arrive at a mirror in space, built specifically to read it. The mirror read it. The number came back at 99.7%. The follow-up data has been collected. The paper is in review. The signal has not disappeared. Let us strip every layer simultaneously. Not the press release, which prioritized caution. Not the most excited version of the headline, which prioritized impact. The actual evidence in the most precise language available. 5 sigma has not been reached. 4 sigma has not been formally announced. 3 sigma is the current level, credible, taken seriously, worth allocating additional resources to test, but not called a discovery. The expected timeline for 5 sigma confirmation, if the detection is genuine, involves specific predictable milestones. The extended NearSpec dataset should raise the NearSpec-only confidence level toward or past 4 sigma if the signal is real, because signal-to-noise scales as the square root of the number of observations. The MIRI results will either show the predicted 9.5 micrometer absorption or not. If both milestones are met, the combined dataset would likely push the overall detection significance to 4 or 5 sigma. The publication of these results, when it comes, will be one of the most important papers in the history of planetary science regardless of what they show. What the honest state of 99.7% comes down to, after everything that can be said has been said, the evidence is asymmetric. It points in one direction. The signal is real in the data. The molecule is produced at scale by only one known process. The planet is in the right environment. The follow-up has not refuted it. The alternative has no demonstrated mechanism. None of these facts individually constitute proof. Together they constitute the strongest case for a biosignature that has ever existed in the scientific literature. Whether that case becomes a confirmed discovery depends on data that has been collected and is currently under analysis. The answer exists. It has not yet been published. The expected timeline for 5 sigma confirmation, if the detection is genuine, involves specific predictable milestones. The extended NIRSpec dataset should raise the NIRSpec-only confidence level toward or past 4 sigma if the signal is real, because signal-to-noise scales as the square root of the number of observations. The MIRI results, if they show the predicted 9.5 micrometer absorption, add an independent line of evidence that's not simply more of the same data. A genuine biosignature appearing in 2 different wavelength ranges with 2 different instruments is qualitatively stronger than the same biosignature appearing in more observations with the same instrument. The combined NIR spec plus MIRI detection, if both are positive, would likely be treated by the community as approaching or exceeding the 5 sigma threshold. The broader lesson of the K218b story, regardless of how it ultimately resolves, is about the structure of scientific progress on questions of maximum importance. We're not searching for evidence of life on K218b with instruments designed specifically for that purpose. We're using a general-purpose infrared space telescope that happens to be precise enough to detect atmospheric molecular features at interstellar distances. Future space observatories designed specifically for biosignature detection would be optimized in ways Webb is not. What K218b represents is the first demonstration that such detection is within the reach of current technology. That demonstration has value regardless of whether the specific detection on K218b holds. If the combined dataset reaches 5 sigma, the scientific community will not immediately declare that life has been found on K218b. The path from confirmed DMS detection at 5 sigma to confirmed biology on K218b requires eliminating the abiotic alternative to a standard of certainty that may take decades of additional laboratory work. The laboratory experiments on Hisian atmosphere photochemistry will need to demonstrate, not merely suggest, that no abiotic pathway reaches the required production rate. 5 sigma is the beginning of the end of the detection question. The interpretation question takes longer. The community will arrive at a consensus position over a period of months to years, not overnight. The honest state of 99.7% is the state of a scientific process at a specific moment. Science is not a collection of final answers, but a process of getting progressively less wrong about questions that matter. The K2-18 BDMS detection is a moment in this process. The retrieval returned the number. The paper survived review, the signal survived independent reanalysis. The follow-up was approved and conducted. The signal survived the follow-up. The lab experiments to test the abiotic alternative are running. The full results are pending. This is where the process is. Not at the beginning, where everything's uncertain, and not at the end, where everything is settled, but in the middle, where the evidence points in one direction, and the remaining uncertainty has a specific structure. What the honest state of 99.7% comes down to, after everything that can be said has been said. The evidence is asymmetric. It points in one direction. The signal is real in the data. The molecule is produced at scale by only one known process. The planet is in the right environment. The follow-up has not refuted it. The alternative has no demonstrated mechanism. None of these facts individually constitute proof. Together they constitute the strongest case for a biosignature that has ever existed in the scientific literature. Whether that case becomes a confirmed discovery depends on data that has been collected and is currently under analysis. The answer exists. It has not yet been published. The 99.7% is a number that arrived in a results table in a 14-page paper in September 2023. It was not in the headlines. It was not in the press release. It was in the body of the science. That is where the real content of any scientific finding lives, not in the framing, but in the data. The data says 99.7%. The source says one thing makes dimethyl sulfide at scale. The planet is in the right place. The follow-up has not erased the signal. That is the honest summary of everything this script has been building toward. The official statement was careful. That carefulness was technical, not evasive. Madhusudan's team understood what they had found and understood what it would mean if it held. They chose the word tentative because the chain from signal to source had one link that the data alone could not close. What they could not do, without contradicting their own paper, was pretend the 99.7% was not attached to a molecule with no confirmed non-biological origin. What 99.7% actually describes is not the probability that something is alive on K2-18b. It describes the confidence level of a detection of a molecule that only one known process produces at scale, in the atmosphere of a world with conditions that process could plausibly operate in, where no competing explanation has been demonstrated. The number is attached to the signal. The signal has not gone away. The abiotic alternative has no mechanism. The follow-up data is consistent. That is the full, honest accounting. The 99.7% is a number that arrived in a results table in a 14-page paper in September 2023. It was not in the headlines. It was not in the press release. It was in the body of the science. That is where the real content of any scientific finding lives, not in the framing but in the data. The data says 99.7%. The source says one thing makes dimethyl sulfide at scale. The planet is in the right place. The follow-up has not erased the signal. That is the honest summary of everything this script has been building toward. What confirmation of life on K2-18b would change, even though it changes nothing about the distance, is the framing of every future night you spend looking up. The stars were always there. The distances were always the same. The physics was always what it is. What would change is whether the lights you see in the sky are windows into a universe where life happens on one world in an otherwise empty cosmos, or windows into a universe where life is a normal feature of the right conditions wherever those conditions arise. Those are two profoundly different universes to live in, even if you can't visit either of them. The investigation is ongoing. That's the most honest thing that can be said. Thank you for following this to the end. A like or subscribe helps this channel find more people who want exactly this kind of evidence-forward investigation. The data is real. The source is unknown.